everyone, my name is Elisa.
My name is Nate.
My name is Tyler.
My name is E.
My name is Sean.
And Tim is not able to make it here today, but we have him off-site. So Tim, if you'd like to introduce yourself. And we are Team Aquanesta. Today we're going to be talking about the Flint, Michigan water treatment facility design that we are proposing. So to give you kind of a background, as you've probably heard in the media, there's been a lot of talk about water corrosion that is happening, lead poisoning of children in Flint, Michigan. And this kind of dates back to April of 2014 when Flint switched their water source from the Lake Huron, which was more of the Detroit area water source, over to the Flint River for economic reasons. They didn't add any anti-corrosion materials for this, so it caused a lot of pipe corrosion, as I said, and because they have lead pipes from a long time ago, that has led to lead poisoning, and this is a huge issue. And so that's what we're going to be talking about. Okay. So you can see the treatment here for the current plant in Flint. We won't go through all of the different things, but you can see it's a pretty standard water treatment design here. It goes through all of the different processes that we've covered. But if you look at the water quality summary, the design flow rate is about 22 million gallons per day. The turbidity kind of ranges from 3 NTU to 20 NTU, and the temperature is very widely ranging, anywhere from 0.5 Celsius to 27.6 Celsius. So that's going to play a huge role in our design of the treatment facility. I won't go through all of the different properties, but you can see those on the right, and so those will also play into our design as well. The jar test results came back, so these are the coagulant aid, flocculation aid, powder activated carbon that we will use, and these are all just sort of what we were found to be the most effective. This is kind of a continuation of that. Flocculation had the highest turbidity at 10 degrees Celsius, so those are the G values that we will be using, settling velocity, filter aid, etc. And now we'll go into the process water treatment, or the proposed water treatment process. We're going to be using a conventional treatment as well, but there will be a sedimentation bypass. So I think I'm handing it off to Tyler, who's going to talk about our flash mix design.
Thank you, Elisa. So, as we all know from the class, there's basically two main design criteria for a flash mix system, that being having a mixing time of less than 1 second and inline mixing. We decided to go with pump diffusion mixing. We found it to be cost effective and didn't require a lot of head loss. So here's just an overview of the calculations that I did. We won't get into this page strictly, but there's a summary on the next slide. So based on the design flow rate of 22 mgd, a raw water velocity of 6 feet per second, and a GT value of 725, we calculated various parameters, such as an inlet pipe diameter, mixing time, which you can see 0.67 seconds is under the 1 second requirement, a required water horsepower, a pump capacity, as well as a required jet velocity, which is in the 20 to 25 feet per second range. We also determined orifice diameter, coagulant feed flow rates, and total dynamic head. So based on those calculations, here's some material selection. Obviously you can't really buy a 32.25 inch diameter cast iron pipe, so we decided to drop that down to 30. For the nozzle, we decided to go with a standard Type H full jet, full cone spraying nozzle from the Spraying Systems Company with an orifice diameter of 3.594 inches, which was extremely close to what we calculated, and withstanding a capacity of up to 825 gallons per minute, and we only needed about 760. As far as the pump, we just needed to meet that capacity again, so we have that. The pump can operate up to 850 gallons per minute, and we decided to implement a streaming current detector to optimize the coagulant dosage. So here's a schematic of the various chemicals that are going to be undergoing flash mixing. As you can see, we have our coagulant down there with a pump, type C because it's scale forming. We also have a lime injection to deal with the hardness in the water, powder activated carbon to deal with taste and odor causing compounds, potassium permanganate to deal with the zebra mussels, and then also adding a corrosion inhibitor at intake to help combat the pipe erosion, not only in the existing pipe distribution system, but also the pipes in the plant. And with that, I'll pass it off to Nate for flocculation.
Thanks, Tyler. So now that we moved through the process of flash mixing, stirring up the wastewater, the intake water, we're going to want to calm that water down via the process of flocculation. So for our design, we went forward with the baffling, not baffling, but using a diffuser wall and the mechanical mixing. This prevents short circuiting because the flow was evenly distributed through the diffuser walls. In addition, like I said before, we're using mechanical propellers to agitate the water throughout the process, and this kind of encourages flocculation. On the right, you'll see a design of our flocculation concept. We went with the 4 trains consisting of 3 stages each. Each stage is a square base, reinforced concrete basin, 17.5 feet by 17.5 feet. Each of these stages will have one vertical shaft flocculator equipped with a variable frequency drive motor for each of them, and at the end we'll have an 8-foot in diameter hydrofoil blade to flocculate the water together. In addition, after each stage we will have a diffuser wall composing of 6-inch diameter orifices. And again, from stage 1 to stage 3, the mixing energy will decrease. Here's just another illustration showing how this the mixing energy will decrease from the different G values of 70 all the way down to 25. We calculated the total head loss for each of these baffle walls, and we could find a Q max head loss and a Q min head loss. In addition, based on the hydrofoils and the RPMs for each stage, we then checked the tip speed at each of these stages and found that it was well below the maximum speed suggested. Moving on to some of the calculations, we won't go too much of it. We were using the calculations taught to us in class. This kind of highlights the orifice size, number of orifices, RPMs, the horsepower of each of these stages. So now that we've talked about some of the flocculation aspects of our design, Sean's going to talk to you about the sedimentation.
Thanks, Nate. So for sedimentation, we had 4 basic design concepts that we had to encounter. So we have long and narrow, the Reynolds number less than 18,000, a Freud number greater than 1/10,000th, and tension time of 4 hours. So here are some general considerations for our sedimentation. We have diffuser wall that's 6 feet from the entrance, it's pretty standard. We have 8 launders. We chose transverse over longitudinal finger types because of even flow. We had the final launder 10 feet from the back wall. We had a freeboard of 2 feet. We had a sludge collection system. We chose to do chain flight over vacuum based on the cold climate in Flint, Michigan. And we had 15 feet wide, 1 for each tank for that. So here are some of our calculations, which I'll highlight in the next slide, but here they are in total. So some of the results I'd like to highlight are the length of the tank, the width of the tank, and the depth of the tank. So we had 17.5 the width and the depth, and a length of 400 feet for our 4 tanks. This gave us a good Reynolds number and Freud number, and a retention time of 4 hours, which is what we desired. So here's a schematic of our drawing. As you can see, we have the 400-foot tank and the 17.5 width, and we also have, as you can see, 75 feet for the total width based on the walls and the tanks. So moving on to filtration, we'll have Tim report from an off-site location on filtration.
So I worked on the filtration section. Here are the filtration concepts. Of course, you all know when you're designing a filter, dual or tri-media, constant level, we went with the gravity rate filtration. Air-water backwash, we were debating whether we needed that or not, but ultimately we decided with it to reduce the amount of water use when backwashing. Here are our calculations. The design plant flow rate, 22 MGD, we were debating between 6 and 4 filters. Now we noticed that population of Flint on the decline. In a 20-year time span, it lost over 33% of its residents. And so, should we build a smaller plant at less cost? But we chose 6 filters because limiting to 4 filters would really hurt the amount of water going through if one filter was, say, being backwashed or was dismantled at one point. And through our L over D calculations, we chose 4.1 feet of our GAC layer, while 1 foot of sand. And we chose 15 foot by 15 foot filter cell areas. So the constructability was also a concern for us, just really simple. And if you move to the next slide, here's some highlights. And after computing the number of troughs, we had 2 troughs per cell. And this is what an aerial view, as well as a side view of our filters would look like. If you notice, we have 3.5 feet between the wall and the filter. That was kind of pushing the 3-foot range, but we thought it would be all right because we did have low turbidity. Also, a thick GAC layer, a sand layer, and a Leopold Type S backwash filter that was at 15 inches.
Well, reach to disinfection. Disinfection is to kill all the harmful bacteria and the microorganics. Also, we check the table to our minimum requires is to a ratio to 3 log infections. When water reaches to disinfection now, we can assume the water pH is 7, around 7, and the flow rate is about 5.4 CFS. So it's quite good. So we choose to use the most effective and the cheapest chemicals is chlorine. So we check it also to check out the table. So we calculate the disinfection volume required from in different weathers. So we find out the winter, when water has the lowest temperature, we require the most volume of the disinfection. But it's not not a large volume, so we decide to mix the chlorine and the water as an inline process. So we add some buffer here to maximize the travel length of the water. So before they reach out to water storage, the most work can be done during the process, during the pipe, in the pipe. Also to make sure it's safe, so we choose to use gas and water injection, so mix the current gas and water before we inject to the processed water. So we think this is the most easiest and effective design. Now, this is our overall process.
So now that we've talked about some of the design components of our treatment plant, we're going to go into what this is actually going to cost to build. So we pulled this cost curve from the late 1800s, I think it was. Not 1800s, 1980s. And then we reflected the cost to whatever the present value would be. So given our planned capacity of the 22 MGD, we could then connect this to the cost within this old cost curve table and then put it into a cost of modern day value. And so by doing this, we found that our plant with the conventional treatment processes would cost $27.4 million based on this cost curve. Looking at the operation and maintenance costs of this, this is another estimation curve. And so based on our plant capacity of 22 million gallons per day, we can then find out that the annual cost for our plant will be around $1.25 million. Using a recommended percentage breakdown of how much each process or each stage of this construction will cost, we highlighted each of these processes in this table here. Again, we didn't want to go too much in depth for each process, breaking it down by each component, because it would be pretty inaccurate, and we would have had to be really conservative and end up being not as accurate as this method. So in total, all these components, from civil work to the clear wells to chemical storage facilities, will cost $27.4 million. So now that we've looked at some of the costs of this treatment plant, Tyler's going to talk about the hydraulic grade line.
Thank you, Nate. So first of all, I'd like to say before we get started in this hydraulic grade line analysis, this is only indicative of when we are in the conventional treatment process stage. As we mentioned prior to this, we do have a sedimentation bypass, so these values do not reflect that stage of the process. So I have it broke down into kind of three sections of the facility. This lists the water elevation and the head loss between storage and the settled water conduit. The second stage is between the settled water conduit and the flocculation inlet, and the third stage is between the raw water intake and the inlet to flocculation. As you can see, we've commuted head loss for various valves, inlets, the flocculation stages are in there, as well as sedimentation and piping during the flash mix process. So here's kind of an overall schematic of what the water elevation is doing. As you can see, in total we have just a little over 13 feet, which is pretty reasonable. So we believe that with head loss we're not going too over or too under, so we should be all right there. Now I'm going to pass it off to Elisa to kind of close things up here.
Thanks, Tyler. So in conclusion, you've seen that each of our treatment processes meets the design requirements. An addition of corrosion inhibitor will combat that future corrosion of the pipes and the infrastructure. This could potentially prevent the need to replace the lead pipes, although we would recommend that if they were to do an infrastructural overhaul, that would be probably long-term a better solution. Conventional treatment with the sedimentation bypass is the best treatment option based on the raw water turbidity that we had, and you can see that it is a pretty standard price tag and processes, and so we believe that this is our best option here. We want to thank you for listening, and we will now open it up to questions. And we will also take online submissions of suggestions and questions, comments after this presentation. Thank you.